Okay, let's begin our treatment of ions with the aluminum atom and the resulting aluminum ion that forms. So aluminum, of course, has 13 protons, and it has 13 electrons, the aluminum atom, and so 2 electrons, 1s2, 2 more electrons in the 2s2, 1, 2, 3. We're going to use 3 rows in the periodic table. The first 2 electrons take us across to helium. The next 2 electrons take us to beryllium. And then we would need to get across to neon by putting 6 electrons, total of 8, into the 2p6, which makes a total of 8 electrons in the second energy level. Then, as we come down to the third energy level, 2 electrons will be in the 3s2 orbital, and 1 electron, as you can see, there are no d electrons, and so we end up here making our 13th electron would be in the 3p1, and so for a total of 3 valence electrons. Now if that's going to turn into the aluminum 3 plus ion, then 3 electrons must be lost. Those, of course, will be lost from the valence shell, or valence energy level, and we would resulting in, of course, 1s2, 2s2, 2p6 as our Al3+. Let's just take a moment and notice that the aluminum atom was approximately this big, and the aluminum ion is, of course, only about that big. Atom, ion. So atom and ion. It's worth noting right now that positive ions are smaller than their parent atom. More on that in the next video. Let's progress to the chlorine atom and the resulting chlorine ion. Chlorine, of course, you can see has 17 protons. First 2 electrons that we need to account for will be in the 1s2. And then the next 2 electrons, first, second, third energy level. The next 2 electrons would be in the s orbital, 2s2. And then to get ourselves across to a 10 total electrons, we need 6 more in the 2p6 orbital. And then to account for 12, 2 electrons would be found in the third energy level in 3s2. And then you can see that there are no d electrons yet. Will exist for a 17 electron atom. And so to get all the way across to account for a total of 17, we would be 3p5. So let's put 8 electrons in the second energy level, p5, which makes for a total of 7 valence electrons. Of course, a reminder that the 7 at the 17, but less the 1, that counts for 10 of the d electrons. This, of course, being the p block. This, of course, being the d block, and the s block. So that would be the chlorine atom. When chlorine turns into an ion, 1 electron needs to be gained. Where's that electron going to end up? Of course, there's space in the third energy level, and that would result in p6. So 1s2, I'll erase that, and end up with our p6. So our electron configuration for the chloride ion, Cl-. Okay, let's make sure I put in the 6 electrons and cause this to be an 8 for our total of 8 valence electrons in the completed energy level chlorine, able to add in the extra 2 electrons. It's worth noting at this time that minus ions are larger than their parent atom. This is because of the extra electrons cause the valence, the 8 valence electrons that are present now, to experience added repulsion. That makes the atom was originally this big, and when the extra electron is put in, the ion will be larger. Again, the atom in green, slightly smaller, chlorine atom, and then the chloride ion will be larger. Now let's finish our treatment of atoms versus ions with the nickel atom and the nickel ion. Nickel, of course, has the ability to form either nickel 2+ or nickel 3+. We'll take a look at both. So nickel, again, let's remember that this would be the S block. This area here is our D block. Let's not forget our P block. Of course, nickel with its 28 protons, we'll put 28, and we'll put the first 2 electrons, which accounts for first 2, into 1s2, and 2 electrons there. Then the next 2 electrons also in the s orbital, 2s2, and then across to account for all 10, we'd finish with 2p6 for a total of 8 in the second energy level. Then if we go down the first, second, third energy level, we would have 3s2, and then proceeding all the way across to argon, we would end up with 3p6. Let's put those in our Bohr diagram, s2p6, for 8 electrons at this point. Now, as we come down to our fourth energy level, we of course are back out to 4s2. And so let's place those electrons on our Bohr diagram. And now, this is where we need to pay attention to the transition between S and D. The next electrons that you might otherwise think should show up out here in the 4p don't. There's enough proton pull at 21 protons to pull what you might expect would be the 4p back into the D. So let's add that in. And it will be 3D because of where they're located and of course we need to get all the way across to 8, 3D8. That would be the nickel atom. Now we could write this as a condensed electron configuration, and this of course could all be represented by argon. If AP asks you to write just an electron configuration, you always would have the option of writing the entire electron configuration or condensed. If they do ask you to write the entire, write the entire. Now, what happens when nickel turns into, let's say, nickel 2+? That is a loss of 2 electrons. And those 2 electrons, I never parked them out here in the fourth energy level, the electrons that will be most vulnerable will be the electrons for being stolen by some nonmetal, will be the electrons in the fourth energy level. So let's say that these electrons are the 2 electrons lost since they are furthest away from the nucleus. And so if we were to finish and write the condensed electron configuration, we might write argon, and then 3D8. Occasionally, you'll see some people write 4S0, but that is not necessary. You can, but you don't have to. What if we wanted to think about nickel 3+, which is an ion that nickel forms? That, of course, would need 1 more electron to be lost. I never did park my 8 electrons back here in the D orbital. And so these electrons are the ones that are removed to make 3D, to make nickel 2+. And now for nickel 3+, it will be a D electron. So we could write argon 3D7. D electrons are higher energy than S and P, and so that's why nickel 3 plus will be a loss of a D electron. Just as before, of course, the nickel atom is larger than the nickel ion because, of course, the atom is larger, and when those valence electrons are lost, then the nickel ion exists in green, which would be smaller.